or let me put it this way. What do you think is the main characteristic of fibrous soil? The main characteristic of fibrous soil. What do you think that is? What do you think would be the main problem or characteristic of fibrous soil? What do you think would be the main characteristic of fibrous soil? Anybody willing to give it a shot? I see a couple of guys. Yeah, that would be one problem. Expanding when it has water or shrinking when it's dry. That is one property. Yeah, agree with that. Okay, that's one. The other property of funded soil will be the issue of permeability. It has very low permeability. Some of these are in the order of 10 to the power negative, close to more than 7, -8, -9 centimeter per second. So very low permeability. So the issue of permeability means the water draining through those soils at a slow rate. Yeah. So then you need to find a way of accelerating the flow of water. Yeah. Now, it wants to bring us back to the topic of consolidation of fibrous soil. I do not have lecture notes for consolidation of soils, but let me see if I can pull a couple of threads for you, and then just stay tuned. Let me see if I can pull a couple of threads for you. You may write your own notes and your own understanding. Giving you some small lecture. Now, we talked about if you have soil saturated and it's clay soil, and you load that soil, this soil will undergo consolidation. All right. Let me get out this thing, minutes. All right. So then what is the process of consolidation? Now, the consolidation occurs in fine-grained soil when you apply loading on that soil. The soil is saturated. Initially, the loading is taken by water. Okay. When you apply loading, it increases the pore water pressure. I hate the way the Word document looks like. I want to get that out. Let me just use my PowerPoint. Let me just use my PowerPoint. I hate the way the Word. Let me just use PowerPoint. All right. So let's say that's saturated clay. That's sandy layer. Now, and you apply loading on that layer. Okay. Now, the clay layer will undergo consolidation settlement. And the consolidation is a process where initially the pore pressure increases due to applied loading. Now, since the clay has very low permeability K, the dissipation of pore water pressure takes a long time. Okay. Takes a long time. All right. Now, until the pore water pressure dissipates, okay, when the pore water has completely dissipated, that's when you say that the consolidation process is complete. Okay? That's when we say that the consolidation process is complete. Now, what do we have? How do we simulate the consolidation process? We simulate this condition from the lab using the odometer test. The odometer test, you prepare saturated sample. Load this sample. Saturated, load it with a particular load. I think it's usually like, let me see, is it 1 kilonewton? 1 kilonewton per meter squared. Why? Initially, that's like a sitting pressure to avoid this soil from swelling. Okay. When the swell stops, then you'll double the load to 2 kilonewton. Now, during that, you, for each and every load, you measure the time and then change in height. Okay, change in height over a period of 24 hours. Start from 0 second, doesn't need height. I think you go 5 seconds, and I think 15, 30 minutes. Okay, these are all in, and then 1 hour, 2 hours, go like that, 4 hours, 8 hours, I think 16 hours, 24 hours, yeah, like that. All right, you have change in height of that sample, okay? And then at 24 hours, it's assumed that there will be no change in height. It will now be constant. Then saturate the sample again, and then double the loading. Double the loading. So you have reading for particular loading. Then now you'll double the loading. Now it goes to 2 kilonewton per meter squared. Take the same reading. 4 kilonewton. Take the same reading. 5 kilonewton, 8 kilonewton per meter squared. take the same reading, 16, after that 32, 64, 128, 256, 512, 1024, probably 2048. So you've taken reading for all this pressure, kilonewton per meter squared. Okay, so each reading you have time was a change in height. Okay, now think about this sample this way. Samples like this, initial height is this, H naught. And then after 24 hours, it's like this, HI. So what is the difference here? That's the settlement of the sample, which in itself is like the change in void ratio, right? The change in void ratio over the original 1 plus E naught, okay? So at each of the reading, you'll calculate the void ratio that corresponds to that loading, okay? You calculate a void ratio that corresponds to each loading, okay? Let's go through how you can calculate the void ratio, yeah? Okay. Change in volume over the original volume, That's the void ratio, right? Now you understand that this sample is restrained to expand laterally. It can only consolidate vertically, right? So in other words, the diameter is not changing, but the length is changing, right? So that's why we consider this volume-wise. Now, once we have all the reading, time and height, or change in thickness of the sample for a range of loading, we can calculate the void ratio for each range of loading. Now let's see, let me get another slide. Now, so for each loading then, we have loading and we'll have void ratio. We'll calculate the void ratio from the original height over the what? The height at 24 hours for each loading. Okay, at 24 hours for each loading, that's what we will use to calculate the we'll use that to calculate the void ratio. So then we can have a plot of the void ratio E and the log of loading pressure. Okay, loading pressure. Okay, and then we'll have something that go make it so nice like that. Something that goes like this. Okay, now we can also begin to unload. After that, unload back to this. You'll find unload back to this, unload back, and then read the change in void ratio as on. Okay, up to maybe up to 4 kilonewton. That would be a slope like that. So this is the unloading slope. Okay, it will not come back to the original void ratio because of soil is not perfectly elastic. Okay, now that is the void ratio versus E. Now the thing is, How do you determine the initial void ratio of that soil before? How would you determine the initial void ratio of that soil before the loading was performed? Let me get somebody's idea. How do you? How do you? Let me get somebody. Hello, ladies and gentlemen. Let me get somebody. Am I still audible? Am I still audible? Before we proceed, that graph. Go ahead. Okay. How do you uh, get the initial void ratio? Tiziano Mwiti. How do you determine the initial void ratio? How can you determine the initial void ratio? Let's do this quick and finish this, man. I wanna wind up this because I don't want to jump into other methods before. How do you determine that? Maybe no. Let me save the day. You know very well that you can get the specific rate of, you can determine the specific rate of the soil particles, okay, and then saturate the sample. When the sample is saturated, determine its water content. You know the saturation will be 100%, and you probably have determined the specific gravity. You know very well the degree of saturation, the water content, specific gravity, plus the initial void ratio. This is 100%. So the initial void ratio with the water content have the specific gravity. Makes sense or doesn't make sense? Makes sense. Before any loading, just saturate the sample. When the sample is completely saturated, determines water content. And you probably know the specific gravity of the particles. So then you'll be able to calculate the initial void ratio. Does it make sense? Good. So we back to this. Let's now get back to this. You have determined this log E versus void ratio versus log of stress in the lab. Now, what's the importance of that thing? What is the importance of that thing? Now, this can help you determine the settlement. Now, let's make it more practical. All right. This is your soil condition. All right. Maybe your sand. Let's say you have a sand here. This sand is 5 meters thick, the density of 18 kilonewton per meter cubed. Then that is the soil, clay. Centimeter thick. There's a density of 20 kilonewton per meter cubed, and it's saturated here. And you did the consolidation testing at the middle of clay layer. In other words, that was 10 meters, that's 5 meters, middle of clay layer. So let's compute the initial effective stress of that clay layer. The initial effective stress at this point A will be 18 times 5 plus 20 minus 9.81 times 5. How much would that be? Okay, 18 times 5 plus 20 minus 9.81. Oh, sorry. 18 times 5 plus 20 minus 9.81 times 5. So that's around 140.95. So 141 kilonewtons per meter squared. Okay, good. And then let's say we built foundation right here. Goes 0.5 meters deep. Okay, and this foundation will carry let's say 200 kilonewton load. The dimension of this foundation is 1 meter by 1 meter. Okay. Now, what will be the change in stress at this depth? If we use 2-to-1 method, then the change in stress at point A would be the loading P over B plus Z into L plus Z. Okay, that would be 200 kilopascal, 200 kilonewton. B is 1 plus, what is the Z? This is 4.5 plus 4.5 kilonewton plus 4 plus 5, that's 9.5 into 1 plus 9.5. So 200 divided by, let me use a 0.5 centimeter. Let me use 0.5. Okay, it's okay. Even now, okay. Let me see. 200 divided by the 9.5. That's 10.5 divided by 10.5. Okay. Let's say it was 2,000 kilonewton. No, 200 is too small. 2,000 kilonewton. Okay, so that will multiply by 10. So that gives us 18 kilonewton per meter squared. So that The initial loading is 141. So let's say you are loading here, maybe 10. I don't know how it would go. Go up to 20. Let me say 100, 1,000, like that all through. So then you'll find of 141 be around here. That's the initial loading. Okay, and then you will now have the final loading is 18. 18 plus 141, it comes to 100 and about 150 kilonewton. So that brings you here, 150 kilonewton. So that's the initial loading is 141 kilonewton, kilopascal. The final loading is 150 kilonewton. So this will be a settlement. That much will be the settlement because that's the change in void ratio. That's the settlement that will be caused by that loading. So that when computing the consolidation settlement, okay, the slope of that line, which is CC, okay, the height or the thickness of the clay layer, 1 plus the initial void ratio, log into the initial stress plus change in stress due to foundation over the initial stress. That's the settlement that you compute. Now, there is one thing that we need to determine from this curve. Soil as a memory, okay? You're able to determine the past stress in which the soil was subjected to. Okay, it's called the pre-consolidation pressure. Now, what happened from the initial tangent, the point of maximum inflation, you're going to draw a straight line. Okay, and then draw tangent to that. Then divide this into 2. Okay, and then from the other slope, bring a line. Let me use this blue line. Bring a line almost straight. Okay, it is going to touch that at this point here. When you give that down here, that becomes the pre-consolidation pressure. That's the maximum stress in which the soil was subjected to in the past. So in other words, if you compare your initial geostatic stress, okay, your initial geostatic stress, the geostatic stress is the soil overburden pressure over the pre-consolidation pressure, that should be able to give you what's known as the OCR. Okay. OCR will determine whether the soil is normally consolidated or the soil is over consolidated. Okay. If OCR is less than 1, soil is over consolidated. If OCR is greater than 1, soil is normally consolidated soil. Okay. You understand? Yeah. And any soil that has an OCR less than 1, that means that the soil will not undergo much consolidation. If it's more than 1, it will undergo a lot of consolidation. Oh, sorry, if it's less than 1, it will undergo more consolidation. That is less than 1. How you calculate the void ratio at 24 hours? Whitney is asking. You calculate from your dial gauge reading, changing height, time at 24 hours. The height has not changed. That's the original height. And then at 24 hours of this height, that much will be the void ratio, okay? Change in volume over the original volume. Over the original volume. You know what the original volume is? You have the diameter of the sample and height of the sample. The change in volume is the change in height over change in diameter. So that gives you the void ratio after 24 hours. So that makes sense. Now, we can also use this 24 hours data for each loading to calculate what is known as the time factor. Okay, what's known as the time factor. No, let me pause. Do you have any question? Do you have any question up to there? Any question? Any question, ladies and gentlemen? Please let me get some response. Any question? OCR is over consolidation ratio. OCR compare the initial stress over the pre-consolidation stress. So then this is the pre-consolidation pressure. So anything around here, any loading, when it's initially static and the final loading around here, soil is over consolidated. Outside here, it's normal consolidated. And normal consolidated soils will undergo very high settlement. All right, now I have to come back again. This CC is the slope of this. The slope of this line. The slope of this line. Okay, it's called the virgin compression line. Okay, that's the edge is the thickness of the clay layer. Now again, suppose your initial loading was right here. Then your final loading is right here. Now you see that now complicates this equation now, because now you have to now get settlement. That complicates the equation now. Let me write now the equation if your final loading was here, because now this loading is beyond the pre-consolidation pressure. Now the settlement becomes, okay, let's say that the loading was here and the pre-consolidation pressure is here. So it becomes, settlement will be CC H 1 over E naught log QP over Q naught plus CR H. Now CR is the slope of the virgin compression curve here. Okay, this is the recompression, this is the virgin compression curve. Okay, 1 plus E naught log the virgin compression curve. It means that it's never been loaded before. Okay, it's not, it's beyond now the past maximum pressure that the soil has experienced. Okay, so that would be Q final. So this is the Q final over QP. Now the equation becomes that. Does it make sense? So they ever cram the formula. It's easy. You're using the loading. The initial loading is within here. The final loading is outside. Then it comes that way. When the initial loading, all the loading are, within. It has not exceeded the pre-consolidation pressure, and that's how the loading is done. Any question? Any question? These things you learn, but looks like you forgot everything. You forgot everything. Any question, ladies and gentlemen? Any question? Any question? Any question? Let me pause and get question from you. Okay. Now probably there's no question. So is this something that you learned in I don't know whether it's cell mechanics 2 or foundation engineering, I don't know which one. Did you learn this? This in soil mechanics 2 or foundation engineering? Hello? Hello? Hello, ladies and gentlemen. Let me get some response from you. Let me get some response. Okay. Mentioned, it was only mentioned, was it taught? Okay. So everything is new. So oh, wow. I don't have the lecture notes for that. I'm just pulling things, whatever I know. I don't have notes for that because I wasn't. I mean, I feel that probably you taught this, so I'm just repeating that so that you can understand. Okay. Now you pick data for like various loading. Okay, and each loading you pick data for 4 hours settlement. A 24 hours change in thickness. So that you can plot. Let me see. Let me see if I can pull. Just give me a second. Let's see if I can pull. Okay. Okay. Let me see. The karaoke. All right. Yes, went away. I'm just pulling something. Let me see if I could get that. Be patient with me. I'm trying to have some stuff that I got from pull that from MIT. I was helping some students from MIT. So let's see. Sure. Let me see. Okay. No, not that. I'm gonna pull that out. It's not the one that I'm looking for. Data from give me a second. For each loading, we got data for 24-hour time period. For 24-hour time period. Now, for each loading stage, we're going to calculate the specimen height, okay, because we have specimen. As we load, the height is changing, right? So the specimen height versus time. Okay. You remember this? For each loading, we got the specimen height and time. Okay, so that time, you'll put time in minutes. You're gonna get a curve like that. Okay, curve like that. Now, we're going to calculate a parameter called CV, and CV is the coefficient of consolidation. So that gives you a time at 90% where the consolidation has occurred. Okay, we usually assume that time at 90%, the consolidation has already occurred, completely occurred. Now, what do? You calculate, you see this slope here? This slope here, calculate, get this, the straight line, draw a straight line to at a point X. then calculate a point 1.15x. So that 1.51x right here, trace it back to the original height of the specimen, where it touches the the change in specimen height time curve that gives you time t9. So this is specimen height versus the root of time. That gives you root 2 t90. Such that the coefficient of consolidation CV is t90 h squared over 90. You know the t90 at where the consolidation curve is 0.84. Now I need to go back. 0.848. The value is 0.4848. Now, the other method would be the Casa Grande method for fitting the coefficient of consolidation. Okay. Now, the Casa Grande method, you do log time versus the height of the specimen. It's going to look something like that. Okay. So, at the tail end, the consolidation is ceasing. So there you'll draw a tangent to that line and a tangent to that line, and it will give you a point t100 where primary consolidation has ceased. Okay? Where the primary consolidation has ceased. Now you know the 100, okay, and the initial compression of the specimen before you started testing. Now halfway that you T50, and the value of T50 will be 0.197. Okay, 0.197. So both will be the coefficient of consolidation. You have T50, the height of the specimen, that will give you the consolidation. Now let's go back to something before I even come back to this, because you never learned this. Like you've said, it's new to you. So things are new to you. Now look here. I said that consolidation occurs when the pore water pressure, when you load this saturated and the loading is initially taken by the water, the pore water pressure increases. Okay, and then it begins the process of this dissipating. Now, the process is completely finished when the pore water pressure has dissipated. Now then, we know what would be the final settlement. So we know what is the final settlement by a certain amount, x. Now, at a given time t, there'll be a settlement, okay, y. Okay. Now, the settlement y over settlement final at x will give you what is known as the degree of consolidation u. How much consolidation has occurred? Okay. How much consolidation has occurred? Now, knowing that, okay, the degree of consolidation. Now, the degree of consolidation u is related to time factor TV. Time factor TV. Now, I'm hearing from you for the first time that you never did that. So let me see if I can get this time factor. You've never seen these curves before. Have you seen those curves before? Have you seen those curves before? It's new. Okay. Another second, let me pull another reference material. That's a little bothering, man. Oh. Did you see this before and you just adding some information for me? Let's see, give me a second. Wow. Okay, I thought I was using this probably just reviewing this, but I'm finding that this is something that probably you haven't had before in the there. Degree of consolidation, how much of consolidation has occurred at a particular time. You never see it. Okay. Now, how much of consolidation has occurred at a particular time? Degree of consolidation. Okay. That is correlated with the degree of consolidation and the time factor. Okay. Now, what is this? When you calculate the time factor, you compare time factor at a particular degree of consolidation, the coefficient of consolidation, and the time that will take for the consolidation to finish. So let's see. Let me do my best and see. So you have a time factor will be the coefficient of consolidation, time it takes for the consolidation to occur over the length of the drainage path squared. Now let's see. If you have a clay, for the example that I gave you, you have sand, clay, and clay. No, and maybe sand. Okay. Now the water molecule here will flow can drain up or drain down. So this is called double drainage. So the HDR here, okay, HDR is the length of the drainage path. HDR is divided by 2. Okay. Now, if in case rock here, if soil only flow up, the molecule here can also flow going up. Therefore, HDR is equals to height. So then, the time it takes for consolidation to occur, this time for single drainage, this is double drainage, this is single drainage. The time will be 4 times. Okay. Now, time factor for which consolidation to cease. The consolidation ceases is 90% degree of consolidation. That corresponds to 0.848. Okay, that corresponds to 0.48. Whew. Man, it's becoming tough to take this thing. I don't have notes of pulling up things for my head. And you haven't done this before. You know what? Let me see if I can get an example. Let me see if I can get an example, probably from. Just be patient with me. Be patient with me. Just be patient. Let me get some patience from you. Okay. Okay. Now, let go through this with you, and then let's see. Can you see that? Can you see that? Your circular foundation is proposed to be constructed in a soil profile 5 meter over sun 7 meter. Okay, the wall is 5 meters. Now, and the soil profile provided, the structural load is 100,000 kilonewton. Now, calculate the vertical effective stress at the middle of the point layer before placing the field. So that then it's a little bit complicated. Not complicated, but the initial vertical stress before middle of clay layer, which is right here. Right here. Okay. So let me see. We have this 16.5 times 5. Somebody punch the values very quickly, and then plus middle here. So we don't know. Oh, okay, it's right here. 12.8 minus 9.8 times, what is that? 15. Okay, 12.5. Somebody punch that value for me, please. Punch that value for me. That's the initial legislative point. Calculate the distribution, the change, the final stress of the present field. So final stress, you can use any method. Okay, I taught you the circular method. You can get that. Okay, Whitney is giving 119, so I'm using 120. The final stress, use the 1-to-1 method, or so not the bulk method or anything. The final stress will be that loading, XF is 0, XF will be 0, and then going downward would be ZF over B would be how many? This is 5 plus 12.5, 17.5 over B is 12, so 1 point something. So you calculate the final stress at that point. The final stress at that point. So let's say you calculate the final stress from the method that I've told you and got the final stress